Section 1.7 Introduction to Proofs. A mathematical system consists of some initial unidentified terms, axioms, definitions, and theorems. Axioms are assumed to be true. The undefined terms are implicitly defined by the axioms. Definitions are used to create new concepts in terms of existing ones. Theorems are propositions that has been proved to be true. An argument that establishes the truth of a theorem is called a proof. An example of mathematical systems are the real number system, the Euclidean geometry, we are not going to study this axiomatic system, but we'll use some examples from real numbers. Theorems often look like this. For all x in a domain, if p of x, then q of x. Instead of one variable, we can have more than one. 2 or 3 or many variables. The first step of the proof usually involves selecting a general element C from the domain and assuming that P of C is true. Subsequent steps of the proof show that Q of C is also true. Finally, universal generalization implies that the theorem for any x, if P of x then Q of x, is true. An example of a theorem is this: for all positive real numbers x and y, if x is bigger than y, then x squared is bigger than y squared. Usually, this is replaced with the following. If x and y are positive real numbers and x is bigger than y, then x squared is bigger than y squared. And we understand the same theorem. Direct proofs. For this theorem, we have n variables. For all x1, x2, and so on, xn in the domain, some domain, which is not specified here. If p of x1, x2, and so on, xn, then q of x1, x2, and so on, xn. A direct proof assumes that p of x1, x2, and so on, xn is true, and using that and previously derived theorems, rule of inference, and axioms, shows directly that q of x1, x2, and so on, xn is true. An example of direct proof: if D is equal to the minimum of D1 and D2, and x is less than or equal to D, then x is less than or equal to D1, and x is less than or equal to D2. Here, D1 and D2 are some real numbers. Proof. We have x less than or equal to D and d is equal to the minimum of d1 and d2, which is, of course, less than or equal to d1. Hence, x is less than or equal to d1. Similarly, d is less than or equal to d2, and therefore x is less than or equal to d2, being less than or equal to d. So establish that x is less than or equal to d1 and x is less than or equal to d2, what was exactly stated here. The next example. Show that the following proposition is false. For any n in Z plus, which is the set of all positive integers, 2 to the power n plus 1 is prime. To show that this is false, we need to find at least one positive integer for which this number is not prime. This is called a counterexample. And we have a counterexample if we select n to be 3. Then 2 cubed plus 1 is 9, and 9 is not prime. Definition. For real numbers a and b, a is bigger than b if and only if a minus b is positive. Example. For real numbers a, c, and d, if a is greater than 0 and c is greater than d, then AC is greater than AD. That is, we can multiply both sides of this inequality by the positive real number A. We get a true inequality again. To prove this, we start with c greater than 0 and c minus d positive. Since this is because c is greater than d, c minus d must be positive. Since a is positive, the product of a and this positive number c minus d is also positive. But the distributive law says that this is equal to AC minus AD. And because this difference is positive, from the definition we know that AC is bigger than AD. Proved by contraposition. These proofs make use of this equivalence. If P then Q is equivalent to if not Q then not P. We know this equivalence from before. And proved by contrapositive is just the direct proof of if not Q, then not P. The direct proof of this is called proof by contrapositive for if P then Q. That is, you assume that not Q is true, and we prove that not P is true. An example of proof by contrapositive is given here. if n is equal to a times b, where a and b are positive integers, then a is less than or equal to root of n, or b is less than or equal to root of n. So we assume that the negation of this is true. The negation of this is written here. The negation of a less than or equal to root of n, or b less than or equal to root of n. We assume that this is true. This negation, as we know, negation of disjunction, is just this. Negate the first part, replace disjunction with conjunction, negate the second part. This is the De Morgan law. Now, what is the negation of a less than or equal to root of n? It is just a greater than root of n. And the negation of b less than or equal to root of n is b greater than root of n. So both these inequalities are true, which means that we can multiply them, multiply the left-hand sides, multiply the right-hand sides, we will get a true inequality. AB greater than root of n times root of n, which is just n. But this means that AB is different from n, which is the negation of n equals AB. So we prove that the negation of the conclusion here implies the negation of this, n equals AB. So this completes the proof by contrapositive. Another example, this example 7. Show that if 100 balls are placed in 9 boxes, some box contains 12 or more balls. This is the same as saying some box contains at least 12 balls. So P here is this part. 100 balls are placed in 9 boxes. Q is some box contains 12 or more balls. We have to show that if P then Q is true, denote the number of balls in box number I by Bi. For I from 1 to 9, we have 9 boxes. Then the proposition P is this: B1 plus B2 plus and so on B9 is equal to 100. Q, the conclusion, means this: there is an I such that Bi is greater than or equal to 12. There is a box number, some box contains at least 12 balls. That is, Bi is at least 12. So, assume that not Q is true. Not Q is the negation of this. The negation, so we apply the generalized De Morgan law. negation goes over the existential quantifier, but it must be replaced with universal quantifier. So we get this equivalence. And the negation of bi greater than or equal to 12 is just bi less than 12. Bi less than 12, here it is strictly less than 12, because bi is an integer number of balls. Bi less than 12 is the same as bi less than or equal to 11. So, not q is equivalent to this. For every I, bi is less than or equal to 11. Which means that we have 9 inequalities like this. This is true for each I, from 1 to 9, which are written, these inequalities are written here. Then we can add all these inequalities. The left-hand sides are added up here. The right-hand sides added gives 99. So b1 plus b2 and so on plus b9 is less than or equal to 99, which means that p is false. P means that the sum of all these b is 100, and here it is not 100. So p is false. Not peace, then true. So we prove that if not q, then not p is true, which means that if p, then q is true. This completes the proof by contrapositive. Sometimes, as in this example, it is more convenient to use proof by contrapositive. In other examples, in other theorems, it is more convenient to use direct proof. Proof by contradiction. Definition of proof. A contradiction is a preposition of the form are and not are, where are is some preposition. Any preposition may be selected here for are if we can prove that are and not are is true. Obviously, this cannot be true. That's why we have a contradiction. Proof by contradiction. To prove that if P then Q is true, we have to prove if P is true, then Q is also true. This is direct proof. We assume that P is true, but Q is false, and derive some contradiction, R and not R. Then we conclude that Q cannot be false, that is, it must be true. And this completes the proof. Very often the contradiction is just this, P and not P. And very often the proof by contradiction may be rearranged to a proof by contraposition. An example of proof by contradiction is example 9. Show that root of 2 is irrational using proof by contradiction. Assume that root of 2 is rational. Then root of 2 can be written as a quotient of two integers in lowest terms, which means that all possible cancellations in this fraction are already done. Particularly, m and 10 cannot be both even. After squaring and multiply by n squared, we obtain this from this, we obtain this equality. This shows that m is even, which means that n is equal to 2 times m1, where m1 is some positive integer. Then we replace here m with 2m1, we get this equality. Squaring and cancelling both sides by 2, we get this, which means, which implies that n is even, and we obtain a contradiction. From one side, R, here R means this, m is even and n is even. In the beginning we had this true, and now we concluded that both numbers are even. So in the beginning, m and 10 are not both even, that is, R bar, not R is true. And here we concluded that both are even, that is, R is true, and this is a contradiction. R is true and not R is true, which is impossible. The contradiction is because we assume something, this thing here, root of 2 is rational. So this assumption is wrong, which means that the negation of this is true. Root of 2 is not rational. Not rational means irrational.